Hi everybody, welcome to Socsci10 discussion number 5. We're going over some probability rules today. I took a look at the homework, tried to figure out what you guys might need to know. This homework is basically practice. A lot of people get probability wrong. It looks like there's a lot of problems, but really this is like how you would go about a math class. You're giving a large set of problems and you work through the problems. And once you do all the problems, you work through the problems, and that practice is going to develop an intuitive understanding of how actually to calculate the probabilities. And if you like to go to Vegas, if you like to gamble or play board games and you're trying to figure out what are your chances, then knowing how to compute these probabilities is very important. And it's just something that you're going to, out of all the math out there that you could learn, that is going to be useful for you in life, being able to calculate the probability of something happening, you're going to find is incredibly useful. Very, very useful. So make sure to do the homework, do all the problems as best as you can, and you're going to find that they're basically just variations on a few simple rules applied in different ways. The homework, it's a bunch of word problems, really. So you're going to read a sentence, you're going to figure out, okay, what kind of rules am I going to apply to this sentence? How am I structure this problem so that I get an answer to these questions? And I'm going to just talk about a few of the rules of probability and kind of give you a basis for how to think about some of these ideas. Okay. So first of all, you can see here I have what's called a Venn diagram. You may have not seen these before. You might just be starting out in college. When I first started seeing Venn diagrams, but you're given these diagrams and basically these overlapping circles. And what these circles, each circle is going to represent, the event of the probability of an event. Okay, probability event. You can think of the whole square that is containing these circles as the universe of probabilities. And looking at the very first square, you can see that the probability of A equals 0.9. That's right. So what you can think of is you can say, okay, the probability of A is 90%, 9 out of 10, or 0.9 is the chance 90% that A occurs out of the universe. So the universe is all of the area shown, not just the area that's colored in, but all of the area in the enclosing rectangle, right? It's a universe of probabilities. And in that universe, A has a chance of occurring of 90%. Now, these diagrams don't necessarily have to be to scale, right? It looks, we know intuitively that the area outside of A and outside of B, the area that's not enclosed by any of these circles, it's much larger than the area in these circles, but it doesn't matter. We're really just using these images to kind of reason about how we can combine these probabilities, right? So in this case, you have the probability of A equals 0.9, okay? And then on the right, you have another circle, probability B is 0.8, right? But how do you combine these? There's a portion of the circles they overlap. Well, what's going on in there? What's going on in there is that's where A is true, right? Probability A is true, but B is true also, right? It's part of the universe of possibilities, part of the area enclosed by the rectangle, and it's the part of the area where both A is true and B is true. This is called the intersection. Okay, it's the intersection. And typically how you get the intersection is the multiplication rule and the rules down below, right? Now these rules, these numbers here, they don't add up exactly, but this is the inverted U, which is the probability of A, and it has a little U shape, right? Followed by B. That means intersection. That's the symbol, mathematical symbol that you'll see used. And what we're doing is we're basically saying where is A and B also true? And there's a couple of different ways to formulate that. The very first way, the true way, is to talk about these conditional probabilities that involve the vertical bar B, right? So the probability of A and B being true is the probability of where they intersect. So you're going to have this intersection symbol, which is the the upside down U. And what you will do is you'll say, well, the probability A and B are true. Well, you got the probability that A is true, right? And then the part of the probability of B being true if A is true, right? So we're looking only in the area that A is true. And we're asking what part of where A is true is B also true. All right? That's what that first line in the multiplication rule means. You can also do it the other way. You could also say, okay, let's just look at what's the probability of B, all right? And then say, what part of in B is A also true, okay? And that is really where you get this intersection from. Now, if A and B are not related events, if they don't depend on each other, right? Then you can just say this intersection is just a multiplication of these two. So if you have two things and you want to know where they intersect, you can just multiply them as long as they're independent events. Now, an independent event is an event that, I'll give you an example of an independent event. Let's say you roll a die. I roll it once, I get a number. And let's say I pick up that die, like a 6-sided die, and I roll it again. I'm going to get another number. I might get the same number, but I'll probably get a different one in all likelihood. But that number, right, the second number I roll, doesn't depend on the first number, right? Whatever the first number rolled, that was the first roll. I'm rolling it again. And the second roll really doesn't have anything to do with what you rolled for the first roll. And that's something that it's just something to understand, because sometimes people will say, I have a 6-sided die here. I've rolled 3 10 times. So what's the probability that I'm going to roll 3 again? People might think, rolling 11 threes in a row. That's very unlikely. But when I roll this die again, it doesn't depend on the previous die rolls, right? Doesn't depend. It's independent of them. So in that case, you could say, well, there's six sides on this die, and the probability any one side rolls up, if it's a fair die, is 1/6, right? And that's not going to change. Now, the probability of rolling 11 threes in a row, that's small, but we're not rolling 11 threes in a row. We're not asking about that probability. We're just asking what the probability that the next die roll that I roll is going to be a 3 after the previous 10 were 3, right? But these are independent events. So if you're going to calculate what that is, these independent events, independent event of rolling a 3 is just 1 in 6, right? But if I have dependent events, it's going to be different. You're going to have to use the above rule. Okay, let's talk about another rule. This is going to be the addition rule, right? A or B. Now, the A or B, that's the addition rule, and that's the top rule there, and that's with the U in between, right? Now, this rule is a little tricky. It's a little tricky to understand, okay? Because what we're really asking about is we want the total area that both circles cover, right? And you can see that the circles overlap. Now, if they overlap, you're going to end up in a situation where the middle part is counted twice, right? So when I look at the probability A, it has that middle part that overlaps with probability B. But when I take into account probability A, I'm counting that middle part. And then when I try to add the probability of B to that, right, I'm going to count that middle part again, even though I've already counted it. I've already counted it in A. So what we need to do is we need to subtract the intersection of these two parts, right? And that's why you can see here the probability A and B is this intersecting area, and we computed that on the first slide, right? I showed you how to compute that on the first slide. But to compute the union of these two probabilities A and B together, we have to remove that middle part. Otherwise, we'll have counted it twice. Count it twice, right? So now, if they're mutually exclusive, See, here is the inverse of are they independent. The mutually exclusive means they are completely separate. So if the A and B circles don't overlap at all, you're not going to count the middle part twice because there's no middle part that is a part of A and B at the same time. They're going to be independent events, or they're mutually exclusive events, excuse me. And what you can do is you can just add A and B together, the probability A and B together, and get that. But if they are overlapping, you have to subtract that middle part. So that's something to keep in mind. And then finally, the probability rule that you're going to use, all probabilities, they exist in a range of 0 to 1. So that's called what is a complement is that, okay, what's the probability of rolling a particular number on a die? Well, that's going to be 1 in 6 because there's 6 different sides on the die. Well, what's the probability of not rolling that number, right? So let's say I have a die and I roll it, and I know that the probability of a 3 coming up is 1 in 6. So what's the probability of not 3 showing up? Well, in a way, this is the addition of the probability of 1 showing up, plus the probability of 2 showing up, plus the probability of 4 showing up, probability 5, and the probability 6. Add those up, right? So this is the union of all the other probability, of the probability of the other numbers showing up. And that's going to be 5 out of 6. But look, we have a shortcut because we know probabilities, they exist between 0 and 1, where 1 is a 100% chance of something happening and 0 is a 0% chance of something happening, right? So we can just subtract the probability of what we are not looking for from 1, and that will give us the remainder. So in the case of a die, where we're asking what's the probability of not rolling a 3, we can just subtract the probability of rolling a 3 from 1, and that will be 1 minus 1 6. It's going to be 5 6. Same number, right? But you can get it 2 ways. You can add up the probability of the events accepting the 1 that you're trying to exclude, or you can just take the 1 you're trying to exclude, that probability itself, and subtract it from 1, and the remainder is going to be the probability of not seeing that event. Okay, now I took a look at the homework, and I'm just going to talk about some basic probabilities here that you're going to need to know in order to do these problems on homework. Okay, so in case you guys don't play cards, you've never played cards before, if you have a deck, a traditional playing card deck, it's got 52 cards. So now if I want to ask, what's the probability that I draw a specific card, right? I want to, the ace of spades. What is the probability to draw the ace of spades from a deck? Well, it's going to be the probability that card is on the top. And there are 52 positions in that deck, right? That card could be anywhere. I don't know where it is. If it's on the top, though, right, I'm going to draw it. What's the probability it's going to be on the top of the deck? Well, it's going to be 1 in 52. Could be there, but it could equally be at any other position in the deck. So that's the probability of drawing a specific card from a deck. But what about if I've drawn a card and it's not the ace of spades, right? I draw something else, 7 of diamonds. So now there's only 51 cards left, right? So what's the probability that the second card I draw from a deck, where I've already drawn one card, right, is going to be the ace of spades? It's going to be 1 in 51 because there are only 51 spaces left, right? So you can think that this is a little different than the rolling a die, because when you roll a die, you always have 6 possibilities. But it's not the same with the deck. Not the same with the deck of cards. Once you've drawn a card, right, you're reducing the number of cards that are remaining. Okay? And similarly, if you look at what's the probability of drawing a suit, a particular suit, like a spade, any spade. Well, there are 13 spades in the deck. So it's going to be the probability, it's going to be the probability, it's going to be 13 out of 52, right? There are 13 cards that could be in the top position out of 52 cards that will result in me getting a spade, right? So there's going to be 13 out of 52. That is going to be the probability of drawing a card from a specific suit. Now, what would be the case if I drew a spade, and now I'm saying, okay, I got a spade, right? What's the probability that the next card I draw is also a spade? Well, there are 51 cards left, but I've already drawn a spade, right? So there's one less spade in the deck. So what would that be? It would be 12 out of 51, right? So you see, I've already drawn one. I drew one spade. And so the number of spades is reduced, but also the number of cards is reduced. Now, if the first card you draw wasn't a spade, it would still be 13, but out of 51, because a card was drawn even though it wasn't a spade. But I haven't reduced the number of spades, so there's still 13 somewhere divided up among the remaining 51 positions. So this gives you an idea of how the denominator and numerator are going to change as the number of cards change and the types of cards you might be looking for. And another probability you're going to need for this homework is, what's the probability of drawing a spade? Not just a particular suit, but a spade itself. Well, there are 4 spades. So again, we have a situation where there's 4 spades that could be in that top spot, and there's 52 spots. So there's going to be 4 in 52 chance. And then as you draw spades or other cards, you're going to reduce the proportion and the mixture is going to change. Number of cards remaining in the deck is going to change. You got to account for that, right? And you're going to need to understand how to apply the previous rules that I discussed about computing what's the probability of one event occurring, right? Drawing a spade, plus the probability of drawing a second spade or maybe a different type of card. You're going to need to understand how to combine these events together by multiplying them or adding them together. If they overlap, you'll need to subtract the middle, right? If you're adding things together. So you just need to keep these in mind and review the chapter note. The chapter book have a lot more detail about these rules, but I'm trying to just give you an idea of an intuitive understanding of how these mixtures change. And of course, if you have a die, if you have a D6, which is Dungeons and Dragons notation for a 6-sided die, D6. The chance of rolling a specific number is 1 in 6. And that's always going to be the case, because when you pick it up, you don't lose numbers on the die. You always have the same probability of rolling, right? So, if I roll 1, it's a 1 in 6 chance of rolling a 1, right? Well, what about if I roll again? What's the probability that I roll 1 in 6, a 1 again? It's going to be another 1/6 chance. But what about if I roll 2 1s in a row? What's that probability? So you have a one event, is 1/6 chance of happening. Another event is also a 1/6 chance of happening, and they're independent, right? They're independent. But I can't give you the answer because that's a question on the homework. Listen, best of luck on this homework. It's a bunch of problems that basically exercise your intuitive understanding of how probability works, how you can formulate these fractions in your mind and combine them in various ways to give you the probability of events happening, given events that have already happened, how events can happen in combination with one another by using OR. Remember, OR and AND are analogs of multiplication and addition, right? So OR is addition, right? We are adding these two regions together, and we might count the center region twice if they're not mutually exclusive. So we have to make sure to subtract that out if they are. And in the case of intersection is multiplication. That's AND, right? Two things. This happens and something else happens. That's really where they intersect, and that is when you're going to use the multiplication rule, okay? And you can see on the right-hand side, we use multiplication and for intersection, and on the left end is similarly for the addition rule, which is OR, right? We're going to take a look at that again. For the addition rule, we're going to for OR you use addition as the base operation. So make sure to review the work the problems. It's some busy work, but it'll work up an intuitive understanding of how to apply this, and believe me, you're going to find this useful going forward if you ever get to Vegas. All right. Good luck on the homework, and I'll see you guys next week.